This is the Unit 5 introduction video for work, power, and energy. When you hear the term work, what do you think of? I think of homework, schoolwork, having to go to work, the work I have to do around the house. But what you don't think about is the physical terms of work. What is actual work in terms of physics? When we saw earlier changing momentum, we saw this as an impulse, and it was applying a force over a certain time interval to cause a change in momentum. Well, momentum is a motion, so that means at the same time you're covering a displacement or a distance. So while you're applying a force over a certain time frame, you're also covering a distance. So whereas impulse looked at the force applied over a time frame, work is going to look at the force applied over a distance. So work is applied force over a total distance, but it's not a division, it's force times distance. So work equals force times distance. So it's the amount of force you apply and the amount of distance you travel. Now this is an interesting idea because a lot of people think that if you were to push on a refrigerator, for example, and you pushed long enough that you worked up a sweat, you did some work. But unless that refrigerator moves, you didn't do any work at all. You just pushed on it. Newton's third law applies there, equal and opposite forces. If it didn't move, you didn't do any work. Now the variable for work is a capital W, and the units are Newton meters, which is force times distance, but Newton meters is also called joules, named after the physicist James Joule. Now power is the rate at which work is done. We hear this commonly as horsepower. My car has a certain amount of horsepower, a truck has a certain amount of horsepower. Power is the amount of work that you can do in a time interval. It's how much force you apply, the distance you travel, and the time it takes. Power is a capital P, it's its variable, and it's work over time. Now, that would be joules per second, which is also called watts. Now, watts, I'm going to give this capital W with the little symbol above it to distinguish it between work, because I don't want those two to be confused. In class on the board, I give work serifs, so it looks like this, in order to distinguish between work and watts. So where do you see watts every day? We see them in our light bulbs. The incandescent bulbs had a wattage. A 120 watt bulb or a 60 watt bulb would give you different amounts of light energy, or light, the amount of work that's done, electrical work, per second. So we use them for those type of power ratings. We use them in vehicles, but we call it horsepower. A truck that has a higher horsepower, like a 350 horsepower, compared to a car that has a 200 horsepower, the truck has more power, can do more work in the same amount of time, which would trace back to the amount of force it applies or the amount of distance it travels. It can use more force or cover more distance with the same amount of force in a certain time frame than another car could. We see work and power a lot of times in simple machines. A simple machine is a device that makes work easier but doesn't reduce the amount of work that you have to do. That's something that a lot of people get confused. It doesn't actually reduce the amount of work you do. It just makes it easier. And we're going to look at how it makes it easier. There are 6 types of simple machines. There's the inclined plane, which is your basic ramp, like moving something onto a truck. There's a wedge, which is used to split wood. A knife is a wedge. A nail is a form of a wedge. A doorstop is a wedge. There's a lever that's used to elevate things or pull things, like a hammer's claw is a lever. Levers are used a lot of times. A seesaw in a playground is a lever. There's another one, a wheel and axle, which is your basic doorknob or your steering wheel in your car. There's the screw, kind of like the screw top on a jar or a lid, or a regular household screw. There's another type that we don't really talk about much in this class, but it's called an Archimedes screw, which is basically the fundamental of a bilge pump, which pumps water from one place lower to another place higher. And the last type is a pulley. And a single pulley by itself isn't actually making work easier, but a compound pulley, which is multiple pulleys in series or in different orientations, can actually make work a lot easier. And we're going to look at the purposes of all these machines and how they actually make work easier. The first simple machine, the lever, is basically an offset board of some sort on a pivot point called a fulcrum. This is the fulcrum right here, which is the pivot point in which this lever will rotate around. Now, the lever doesn't just go up and down, it actually goes around in a circle because this pivot creates a radius, and this lever, if you would move it, would go around in a circle. But when we deal with it, we mostly deal with the vertical displacement of both sides. Now, when this lever has been moved up or down, let's say the blue is the new lever. If I was to move it downward and upward here, this will actually create a distance here in red and a distance here in red, and you'll have to use different forces on either side. This longer distance over on this side will require less force than this shorter distance on this side. This is where you typically place your load, or whatever the thing is you're trying to lift. If you're trying to lift up a car or some type of furniture or something, this is where you would place it with the fulcrum near it, and this longer distance that you travel created by the longer radius would use less force. An inclined plane does a similar task. By placing an object on an inclined plane and moving it up the plane, you actually travel this long distance instead of this short distance. So by lifting something straight vertical, I have to do a certain amount of work to get it up there. I can take that distance I travel and extend it over a longer ramp, so I use less force to push it up there. That force would be the weight of the object and the angle of this ramp, similar to the parallel component of the force that we saw on an inclined plane. Actually, it is the parallel component that we saw. So by reducing the angle of the ramp, I can lengthen that ramp and thus reduce the amount of force that's needed to push an object up the ramp. We commonly use this for handicap ramps, for example. I think in Massachusetts the code for a handicap ramp is 12 feet of length for every 1 foot of height. So that dramatically changes the amount of force that you need in order to lift an object up 1 foot by extending it over 12 feet. The last one is the wedge, which is shaped like this. And the wedge moves towards the point. So what it does is, by pushing this distance down, you actually separate something that smaller distance across. So if this was a piece of wood that I was pushing the wedge into, I'm pushing the wedge in a longer distance than I'm separating the wood. So by pushing a farther distance in, I can get a small separation of the wood on the top, but it's still easier than if I was to try to grab that wood by my hands and try to pry it apart by myself. We use this type of simple machine for cutting things, like a knife. If you look at the very edge of the knife where the tip is, where the sharp part of the blade is, that's a wedge. A nail, the very tip of a nail, is a wedge as it pushes itself through. A doorstop is a wedge that, let's say this is the door. When you push that wedge in, by pushing the wedge inward a certain distance, you actually just push the door up just a little bit, and that creates friction in the hinges, which can help keep a door, and friction between the ground and the door, and the wedge, which keeps the door wherever you want it to be. So these are the first three types that deal with kind of straight distances. The next couple of simple machines deal with more of a circular motion. Okay, a pulley is a simple machine that can do multiple things. The first thing that a pulley can do is it can change the direction that you're trying to move something or trying to apply a force. Let's say this is my pulley, and I have attached to it a weight hanging down. What that pulley will do is it will extend the rope around the pulley and come down this way, so I can apply a force downward to lift the crate. So I can use maybe my own weight downward to lift the crate upward. Now that doesn't apply any advantage to this machine. It doesn't make work easier, but it does change the direction of the force so that I can I can lift this object without having to use any other devices. Now, a compound pulley For example, let's say that's the ceiling and I have a rope attached. I'm just drawing a couple pulleys here. This pulley right here that I'm drawing right now just changes direction. This one actually has a weight attached to it. So what will happen is when I pull down on this rope, this pulley is stationary. This one is actually going to travel upwards. And when it does, it will lift this object up with it. But by doing so, I actually have two ropes here holding this one object up. It's kind of like you holding your weight up with two arms. Each one of these ropes now has 50% of the weight. This one's attached to a wall, this one's attached to another pulley. So as I pull this rope downward, this rope's going to work its way through, and I only have to use half the force that I would need to lift this object because I'm splitting it over two ropes, and I'm allowing this pulley to move. Now, wheel and axle. Wheel and axle relies upon the radius of the wheel and the radius of the axle. For instance, your steering wheel in your car has a very small axle in the middle and a larger wheel around the outside. And I could use a very large amount of force to turn this axle, let's say halfway, or I could use less force over a longer distance to turn this wheel halfway. If I was to try to take the steering wheel off my car and just grip the axle and try to turn it, it would be a lot harder because the radius of the wheel is a lot smaller than the radius of the axle is a lot smaller than the radius of the wheel. So the wheel gives me a longer distance. If you notice in buses are a lot heavier of objects with bigger tires and they're harder to turn. So the wheel is a lot bigger. The wheel in a bus is actually several feet wide. The wheel in a car is only about 1.5 feet, if that wide. In a truck, it's a little bigger. And if you look on a ship, like a pirate ship or something, the wheels are huge because they need more of a distance because they have more force that they have to move. Now the last one is a screw. A screw is basically an inclined plane wrapped around a central axle. If you look at a screw, it has these treads on it that go up it. And by turning the screw in a clockwise or counterclockwise motion, you actually extend the amount of distance that this thing is traveling. Instead of going straight down, you're actually going in a longer distance around and around and around. So it's almost like an inclined plane around a center pole. You see this like a spiral staircase, for example, is technically an inclined plane, but once you wrap it around a pole and create a spiral staircase, it's now a screw. Screws are used for multiple things. You get that inclined plane, that's a lot of friction on a flat surface, and if you can wrap it around that central axis, you now have a ton of friction to hold things in place. So we use screws to hold wood together and cars together and metal and stuff like that. A screw can also be used as a pump. The one I was talking about earlier, the Archimedes screw, is actually a screw that's placed inside a tube and it's slightly angled downward. You've got a crank up top here that you can turn. So you can take that crank and you can turn it in a circle a couple times. And there's a hole down at the bottom that allows water in. So let's say I have water up here. It'll allow water in. And as I turn this, it creates a gap right here that collects water. And as it turns upwards, this screw that is fit snugly inside that tube doesn't allow the water back down. And there's a hole at the top, and that water will actually spill out at the top. You can go on YouTube and look up Archimedes screw and see this actually work. A lot of times they use this in reverse with water flowing down from a river, above a river to below a river, like at a dam, to create power, because that screw can turn a turbine, and that's constant flow of power. They use these in the ocean called tidal barrages to turn screws as the tide comes in and the tide goes out to turn a generator. So the simple screw has a lot of multiple functions you can use for it. So like I said, the purpose of a simple machine is not to increase or decrease the work, it's to multiply either the force or the distance, but never at the same time. You can never do both at the same time because that would change the amount of work that you've done. So if I take a simple machine and I double the amount of distance that I apply the force, I will half the amount of force that I need so that the product of the force and the distance comes out the same. So that's the purpose. is to reduce the amount of force needed by increasing the distance the work is done over. So how much does a machine reduce the amount of force that you need? How much does it make it easier to move something? That's called mechanical advantage. If you say that I can do something 2 times better than you, you're talking about my advantage, how much easier it is for me to do things. The quantity of measure that multiplies force or distance is called this mechanical advantage. Now, it relies upon the distances that you travel and the forces that are applied. Forces have the problem of always having friction present. We'll get to that in just a little bit. The mechanical advantage, MA, is the ratio of forces involved. So the amount of force that I have to use to turn something and the amount of force that the object resists with. Ideal mechanical advantage, IMA, is the same thing. It's mechanical advantage. But ideally, if we want to get rid of friction and any of the problems, we'd be dealing with distances. So we'll look at these two, how mechanical advantage can be used in forces and distances to create an ideal machine or a regular, normal, everyday machine. So mechanical advantage is the ratio of the output force over the input force, how much you get out of it versus how much you put into it. And it's also the ratio of the input distance over the output distance. Now these are opposites because, like we said, or like I said in the other slide, you can't have both increasing at the same time. So as I increase my output force, my output distance would decrease. They're inverses of each other. So my mechanical advantage is either ratio of my output force over my input force, or my mechanical advantage is the ratio of my input distance over my output distance. The only reason I call distances IMA is because ideally they don't deal with friction or any other forces, but it's still mechanical advantage. Now if I want to look at this from a different perspective, from a perspective of what I have to do and what the object does, I can look at it in terms of effort and resistance. Effort is what I do, resistance is what the object does. So if I'm trying to lift something with a lever, the effort that I push with, let's draw it over here. Here's my lever. This side that I push on is my effort side. This side that the object will resist with is my resistance side. So my effort distance is over here, my effort force is over here, my resistance force is over here, and my resistance distance is over here. So mechanical advantage is a ratio of the force of the resistance, the weight of an object or something like that, and the effort force, what I apply. Now this is where this resistance force is also where the friction is involved. The ideal mechanical advantage deals with the effort distance, what I do, over the resistance distance, what the object does. This does not involve friction, so it's ideal advantage. Now, mechanical advantage, by the way, has no units. It's a ratio of forces or distances, so units cancel. It's just a factor. When we talk about the advantage of a machine, a lot of times we're talking about the efficiency. How efficient is a machine? There's no perfectly efficient machines because all machines deal with some type of rubbing or contact, which means friction, and friction means heat. That's why if you've ever tried to pull a nail out of a board really fast and then touch the nail, it's actually hot because there's a lot of friction there. If you slide something up an inclined plane, you'll create friction and heat. A lot of times pulleys, you'll see in movies, if something's turning a pulley real fast, they'll create a lot of friction inside the central pivot point, the axle. There's no such thing as a perfectly efficient machine. So we have to look at efficiency. Efficiency of a machine is the ratio of the output work, what you get out of it, compared to what you put into it. Now, you get out less than you put in because of friction, so you're going to get a number less than 100%. If we multiply this ratio by 100, we get a percentage. So efficiency is output work over input work times 100. Now, if you think about vehicles, for example, your normal bicycle is about 70% efficient, which means you lose about 30% of your work to friction and heat. You don't actually, well, it's not really lost. You can't create or destroy this type of value, but it can be transferred into friction. If you look at an automotive vehicle, your normal car is only about 23 to 25% efficient, which means, let's say it's 25%. It means if you're paying $4 a gallon for gasoline, only one of those dollars is actually causing your motion. The other $3 is causing heat and friction, and it's lost to heating up your engine and the environment around you. So you're really paying quite a bit just to heat up the air and heat up your car instead of actually moving you. So kind of just a summary of what I just said. An ideal machine, your output and your input work are equal and there's 100% efficiency with no loss. Real actual machines, less than 100% efficiency. Your output work is less than your input work because you lose some of that work to friction and heat. The ideal advantage can be seen with the distances though. If you do your IMA, your mechanical advantage with distances, you'll be seeing what the machine would be like if it was ideal. If you then do it with your forces, now you see what it would be like with friction. Our next topic is torque. Torque is work. It's just work that's done in a circle. It's the same idea, it's the same formula. Distance that you travel in a circle is called circumference, but circumference depends upon radius. Circumference is 2 pi r, so it depends upon the radius of your circle. This radius is what we call lever arm, so we don't have to worry about how many times we turn it. We can look at the measurement of that circle. So it's called lever arm because let's say I have a lever right here. If I turn this lever arm, it's actually going to go in a circle based on this radius right here. So this is my lever arm. It doesn't matter how many times I look at that circle. If I was to do the other lever arm right here, it travels in a circle as well. Now I have a wheel and axle. My lever has become a wheel and axle, and this is a smaller lever arm right here. So instead of looking at the circumference and how far I've gone, I'm looking at the ratio of these two lever arms. But for torque in general, I'm just looking at the lever arm itself. So if work was force times distance, then torque is force times lever arm, where this lever arm is your distance. So for a wheel and axle, like I just showed on the last slide, here's my wheel, here's my axle, here's my central point. For a wheel, this is your lever arm. And for the axle, this is your lever arm. So obviously, this lever arm for your wheel is your effort distance, and this lever arm for your axle is your resistance distance. So by showing that you have a longer radius for your effort, you would have a longer circumference for your effort. Shorter radius for your distance, for your resistance would create a shorter circumference. So I would apply less force for a longer lever arm, turn this wheel and axle. Now for a lever, like I showed just a second ago, it's the same idea. I have this lever arm right here in red, and this lever arm in blue. This is where my effort would be. This is where my resistance would be. And like I said, a lever is basically a wheel and axle just in the shape of a board. It goes around in circles. But we're looking at these two different arms as to what I would use for torque instead of the circumference of the circle. Torque can be used to balance objects. It's why tightrope walkers use a long pole to balance themselves, because they can create different torques on either side. This is what happens when an ice skater pulls their arms in close or moves them far away. It's the same idea as if you were trying to lift your grocery bags. If you lift them close to yourself, it's pretty easy, but if you extend your arm out far, it now becomes harder. If you're on a seesaw and I move the pivot point, it becomes harder to move somebody the farther away they get. So this example, for instance, if I place an object that has a mass of 45 grams 5 meters away from a resistance point, from a fulcrum, I would only need the weight of another object that has a mass of 22.5 grams if I double the distance. So if I double this lever arm, I only have to half the weight in order to hold it in place. You have force times lever arm and force times lever arm. The force here is equal to weight, which is equal to mass times gravity. So the weight of this object over here is half the weight of the other one because I've got double the lever arm. This is how a crane works. Your basic crane that you see on a construction yard. Let me see if I can draw this without going off the page. Your basic crane lifts very heavy objects. Now that's a lot of torque right there. From the crane to the end of the arm, that's a lot of torque. That's a very long lever arm. So what they do is they place this movable object on the back of the crane that can move back and forth. It's called a counterweight. And this counterweight can increase the torque on the other side, thus creating a pivot point on the crane right here. So this lever arm with this weight is equal to this lever arm with its weight, the counterweight, to help balance this thing so the whole crane doesn't go topple over. You see this a lot actually. My grandfather used to have a tractor, and he'd have a big bucket full of rocks on the back of the tractor, so when he lifted something up with the bucket, it didn't topple the tractor forward. Torque is also what we use for removing nuts and bolts from cars, trucks, other pieces of equipment. This bolt right here is being turned. If you were to try to turn this by hand, you're turning the radius of the bolt, which is a very, very small lever arm. You would need a lot of force. But if you extend this wrench out to be a foot, you could provide a certain amount of force, which in this diagram is labeled as 20 pounds. If you go double the distance out, double the lever arm, use half the amount of force, only 10 pounds. If I was to go out even farther, I could use less force. If you have a wrench that's not long enough, one thing you can do is put a bar on it, like slide a bar on top of the wrench and extend that wrench out farther. Now it becomes very easy to turn something. The last topic of this unit is energy. Energy is the ability to do work. Now, energy isn't something that you can actually store or keep or have or save, or you can't taste it or touch it or smell it. Like an energy drink doesn't actually have liquid energy in it. Energy isn't strawberry flavored or weird candy flavored. Energy is an ability to do work based on certain characteristics of an object. There's two main types that we're going to talk about. They're called mechanical energy. Mechanical energy deals with potential energy, which is energy due to position, composition, or compression. By position, I mean if you were to lift an object on top of a roof, it could then fall to the ground, which means based on its position, work could be done on it. There's an ability for work to be done on it as this object falls to the ground. Composition is like chemicals. A battery has the ability to do electrical work based on the chemical reactions that could happen inside of it. Compression is like if you drop a ball on the ground. When it hits the ground, it will actually compress the rubber or whatever material you're using. And now there's the ability to do work in the opposite direction based on that compression. It's kind of like a spring. There's the ability to do work. Doesn't mean it's actually being done, but the ability is there. Kinetic energy is the energy of motion. It's the energy that's actually being used as an object falls or as it rebounds from being compressed. Now for energy, the units that we're going to use are joules, which means they're the same units as work. Energy is the ability to do work. It's the amount of work that's being done or how much work could be done. So it's kind of like impulse was the amount of momentum you change. They have the same units. Energy is the amount of work that could be done or is done. They have the same units. For potential energy, we're going to deal with gravitational potential energy in this class, objects that are dealing with gravity and being dropped or elevated. So it deals with an object's weight and its elevated height. If I lift a 5 Newton object 3 meters up, I've increased its potential energy. Work done to lift an object to a height is the same as the amount of energy needed to bring it to that height or to bring it back down. So if I do 5 joules of work to lift an object, that means I've given it 5 joules of potential energy. It has the potential to do 5 joules of work as it comes back down. Doesn't mean it will, but it has the potential to do it. Now, if you think of potential energy in terms of reference frame, When I said energy isn't something that you can store or keep, it's not an actual physical thing. It's an ability. If you think of an object that is put on your desk, in terms of that object and the floor, from that perspective, there's an ability for that object to fall, to do work, which means energy could be supplied. So there's energy there. But if you think about it in terms of the object and the desk, there's no more distance the object could fall down to the desk. So there's no energy there, there's no potential energy. So how can you have and not have something at the same time? So energy can't be a physical, actual thing. You can't have and not have a physical thing at the same time. So energy is the ability to do work based on your location or your position. Gravitational potential energy is shown as the formula mgh. Now if you remember, work was force times distance. If I lift an object up, the amount of work that I'm doing is equal to the weight of the object times the height in which I'm lifting it. Weight, if you remember, was mass times gravity. So when I combine these two, the work is equal to the force times the distance, but the potential energy I provide is equal to the weight, which is mass times gravity, times the height of the object. So these two are the same idea. So for gravitational potential energy, the potential energy is the amount of work that I do or could have done on it, and the mass and gravity's acceleration are my weight, and the height is the distance that I've traveled. Now, kinetic energy is a little more involved. If you think about it, kinetic energy is the energy of motion. It's a moving object. Moving objects have velocity, they have momentum, it deals with the object's mass. The amount of work that you have to do is the amount of force you have to push something. The more mass you have, the more force you need to push it. And it has the formula 1/2 mv squared. And what I'm going to do right now is show you where that formula comes from, the derivation. If you remember this formula, this is our time-independent motion formula. It deals with velocities, accelerations, and displacements. I'm going to use this to create the kinetic energy formula, 1/2 mv squared, by incorporating these two along with work being done. The first thing I need to do is get mass and force involved into this equation. What I've done here is I've used my simple force formula, F equals ma, rearranged it and substituted F over m for acceleration. So force over mass, I substituted for acceleration. This is by using my basic net force formula. I did a couple of steps here. I divided both sides by 2 to get the 2 out of the right side, and I multiplied both sides by mass to get the mass out of this equation. So I'm left with force times distance over here, and m times vf squared minus vi squared over 2 over here. Now I just have to clean that up. Now that I have the left side cleaned up, I have 1/2 m vf squared minus 1/2 m vi squared equals to the amount of work that's done. So the amount of work that I did is equal to the difference of these two quantities. Work is a force over a distance, and a force will accelerate you. So if I'm accelerating, I'm changing my momentum. So I'm going from one momentum to another. So I'm changing my velocity. I'm also changing the amount of energy that is provided to the object by increasing its velocity. So if increasing the velocity changes the momentum, which changes the amount of work that was done, or shows the amount of work that was done, it changes the amount of energy I have, because energy is the ability to do work, which means one of these, just one single one, is my kinetic energy. That means the amount of work that was actually done is the difference of my two kinetic energies. Go from one energy to another, work must have been done. So, kinetic energy is 1/2 mv squared. Now there is a conservation law we have to look at here, conservation of energy. You cannot create or destroy energy. It can only be transferred or transformed. Chemical energy can be transformed into electricity or motion. Mechanical energy can be transformed into potential energy or friction or heat. You can't destroy it or create it, but you can transform it or transfer it. The conservation of energy for kinetic energy and potential energy can be shown simply by a pendulum. A pendulum is an object that has a central pivot point, and that object swings back and forth. and back and forth. At the top of its swing, it has no velocity. Then you release it and it starts to accelerate downward. It's at its fastest at the bottom and then slows down again to the top. So it accelerates and slows, accelerates and slows. We'll look at this example in class on Wednesday. At the top of its swing, where there's no velocity, there's no kinetic energy. But it does have its maximum gravitational potential energy up here. It's not going any higher. It's been lifted to its highest height that it can be at. When it starts to swing downwards, once it gets to the bottom, there's no farther down it can go, which means it has no more potential energy. All that potential energy from above has been transferred into kinetic energy. Once you reach the maximum kinetic energy, you've now reached the maximum velocity. So the maximum velocity of a pendulum is at the bottom. So you start at zero velocity to maximum velocity to zero velocity to maximum velocity and back and forth. Now if there's no friction present in this system, this thing will go on forever, back and forth. If there's no loss of energy due to friction, this thing will just keep going. And friction by air resistance or by friction up in the pivot point. But since there is friction present, we have what's called a dampening effect, which means this pendulum will lose its height continually over time until it comes to a stop. And that's what we experience with grandfather clocks and things like that. They need a motor to keep driving them, to keep them going, to overcome the friction. The last thing I want to talk about is a roller coaster. A roller coaster has some device, a chain or something, to drag you up a hill at the top. Gets you up there, applies a force over distance. Once you're at the top, you have a lot of potential energy. When you start to fall, that potential is transferred into kinetic energy, which is why your velocity increases. As long as you don't go back up to the same height, you have kinetic energy. You can go up another small hill, which means you lose some kinetic energy and gain some potential, which is why you slow down. You can go down another hill and come back up. As long as you don't go up to the original height, you can keep transferring that potential into kinetic and back and forth to keep you going up and down all these hills. A lot of times, they might even throw a loop in there. As long as the loop has enough potential energy from the beginning to provide it with enough kinetic at the bottom, you'll make it around. So there's an example, there's a question in your homework that deals with this. I think it's one of the synthesis problems. Just remember that as you lose potential energy, you gain kinetic energy, but the total energy of the system is always equal.